This is Dr. Lusher, and this is a video about stoichiometry involving gases. And it'll be helpful for you not only in working on these problems, but also on one of your pre-lab problems for Lab 3B. So we've done a bunch of stoichiometry calculations now, and they can be done for anything: solids, liquids, gases, solutions. Every time you do a stoichiometry problem, you have to be comparing moles of reactants and products. That's the key to all stoichiometry problems. With gases, we often don't have the mass of a gas. It's not as easy as a solid to put on a balance, but we have a really powerful tool at our disposal, and that's the ideal gas equation, PV equals nRT. And if we rearrange that for n, we can solve for the number of moles of a gas if we have pressure, volume, and temperature of that gas, along with R, the ideal gas constant. So here's our stoichiometry map that we've seen before. We're adding a new possibility to it, and that's that when we know the pressure, volume, and temperature of a gas, we can solve for the number of moles. And pressure, volume, and temperature are fairly easy to measure with a gas. So that can be our starting point that allows us to calculate the number of moles, and that's always kind of our first step of a stoichiometry problem. Equally, on the unknown side of the stoichiometry map, once we solve for a number, however many moles we might have of a product in a stoichiometry problem, we can solve for pressure, volume, or temperature. We already have N from the stoichiometry, and then maybe we have the volume or the temperature or the pressure, and we can solve for whatever we don't have. So let's do some practice. Best way to learn this stuff is to do some problems. And this problem is on page 8 of your Chapter 5 lecture notes. So you do have it in front of you. And it's a reaction of two methane molecules that are heated, pressurized, and that is how acetylene is produced, which is also known as Welder's gas. And it also produces hydrogen. Now I want you guys to look at this reaction carefully. We're starting out with two molecules, or 2 moles, and when they combine, we end up with more molecules. We have 1 mole of acetylene, but we have these 3 molecules of hydrogen. So we went from a total of 2 to a total of 4 molecules. That's going to have an impact on this problem. So the problem is asking for the total mass of acetylene that can be produced, and then also the pressure of the reactor once the reaction's over. So the given information is that this vessel is 50 liters. Initially, it's filled with methane, CH4, at 10 atms of pressure and 298 Kelvin. Then it gets heated and the reaction happens. So let's think about a strategy for this problem, and let's use our stoichiometry map. So what's our given and what's our unknown? Well, our given is that we're starting with methane. We have measurements about the methane in this reaction, and we're going to use that to calculate the mass of one of the products that's produced. So we'll start with our pressure, volume, and temperature of methane. That'll allow us to calculate moles of methane that are reacting. We'll use a stoichiometric ratio to calculate moles of our products, and then we'll just need to think about the acetylene to get its mass, but then for the new pressure of this whole system, we'll have to think about all of the products. So we'll talk about that as we get there. So step 1 is get to moles. Now there's a couple temperatures in this problem, so you might not be sure which to use, so you need to do some thinking here. The volume was 50 liters, the pressure was 10 atms. 2 temperatures were given, but what's really able to quantify the initial moles of methane is that temperature that it's starting out at, because that's sort of what the conditions were when the vessel was loaded with the initial amount of methane. So we can use the rearrangement of the ideal gas law to plug in 10 atms, 50 liters, our gas constant, and the temperature. And you should see here that all these liters, atmospheres, and kelvins are canceling. And when we complete the calculation, we end up with 20.4 moles of methane. So we have now moved from the yellow box to the blue box here. We have 20.4 moles of methane. Step 2, use our stoichiometric ratios to determine the unknown moles. So we know we're going to have to figure out the mass of acetylene, so we definitely need our moles of acetylene. And it's a 1:2 ratio, so we end up with 10.2 moles of acetylene. Now, the hydrogen is important because that's affecting the pressure of the vessel at the end of the reaction. There's 3 moles hydrogen for every 2 moles methane, so we're getting a whole bunch of moles of hydrogen gas here. Not a bad idea to work on an ice table for a reaction like this. And we can just keep track of all our molar amounts as they're changing with an ice table. Challenging to keep track of 2 products, but an ice table makes it nice and clear. We've got our 10.2 moles of acetylene, our 30.6 moles of hydrogen. So yeah, we figured out how many moles of these products we have. Step 3 is, what do we actually need to quantify about these products? So the first thing is the mass of acetylene. And this part is relatively straightforward. We've already calculated our moles of acetylene, did this step on a previous slide. Now we just need to do a molar mass conversion. So we end up with 266 grams of acetylene. Now the pressure, what's going into this pressure of the final reactor? We want to use the ideal gas equation. We want to make a list of those variables. And like I said, it's both the acetylene and the hydrogen that are pressurizing this vessel at the end of the reaction. So it's still 50 liters. It didn't say anything about the vessel changing volume. The temperature at the reaction is 1600 Kelvin, so that's our temperature. And then our moles are the sum of the moles of both products, and so that's 40.8 moles. We'll keep talking about this, but gases, it doesn't really matter whether it's acetylene or hydrogen or something else. They kind of all behave in the same way, so we can complete this ideal gas law calculation just using the total amount of moles of gas. And from there, it's simply plugging into the equation solving for P. So we've got our N, our R, our T, and dividing by our volume to give us 107 atms of pressure. So I mentioned that this is a technique that we can use for a pre-lab question, and I'm not going to do the whole question for you, but I do want to talk about it and map out kind of a strategy. So if you haven't looked at the pre-lab questions yet, you might want to do that before watching the video. Or before completing this video, but you guys on Wednesday or Thursday will be collecting hydrogen gas that's produced in a reaction. And you only want to make 20 mils of hydrogen gas, or else you're going to overflow your gas collecting tube, a burette tube. So you're asked to calculate the mass of magnesium metal needed for these 20 mils of hydrogen gas. And you're asked to assume a temperature and pressure that you think would be close to the conditions of the lab. So let's think about this. Key question, and sometimes a challenging question, is what's our given and what's our unknown? So even though in the reaction you'll be starting with magnesium, for this calculation you've got a target, and that's this 20 mils of hydrogen gas. So that's your given in this problem. The unknown is the magnesium, because you're asked to calculate how much magnesium should we use. So that's our unknown. And since the hydrogen is a gas, we're able to use the ideal gas equation. We have a volume we're targeting, and we can assume a pressure and temperature. So that's enough information to solve for the number of moles of hydrogen that we want to generate in this reaction. And then we can use a stoichiometric ratio to calculate the moles of magnesium, and from there a molar mass calculation to calculate the mass of magnesium required.